Hi everyone, my name is Clément Cannon and I'm going to talk about the randomness complexity of differential privacy. This is joint work with Francis Su from Harvey Mudd College and Salil Vadan from Harvard University. And this is a paper to be presented at ITCS 2025. So I'm going to start with a definition that most of you or many of you might have seen already, that of differential privacy, as introduced by Dwork, McSherry, Nissim, and Smith in 2006. So if you haven't seen this definition before, essentially what this is saying is that a randomized algorithm is epsilon delta differentially private for some parameters epsilon and delta that quantify exactly what privacy means. If for all neighboring databases, datasets, X and X prime, and all events E, the probability that the algorithm outputs something in E on input X is not too different from the probability that that algorithm outputs something in the same event on input X prime, which is pictorially depicted by the two little Gaussians that look like each other at the bottom. So again, if you haven't seen that before, don't be too worried about it. But the important thing is the keyword randomized here. So a randomized algorithm M is differentially private if essentially on two databases that are like not too different, the distribution of the output is not too different. And this has been a very successful definition since its introduction that has been used in many places as essentially or at least one of the key right ways to capture what being private is. Now, one question is, this is a definition, how do we achieve it? And thankfully, we have many techniques to create and to build differentially private algorithms. And many of them, at a very, very simplified and high-level view, they work by injecting some carefully calibrated random noise to whatever they compute. And so many of those techniques are called mechanisms, but think of them as algorithms. This is the same thing. So we have the Laplace mechanism, the Gaussian mechanism, the Poisson mechanism, which correspond to different types of noise you can add to what you're computing. There are things that are just not adding noise, but something like the exponential mechanism. And we have many, many other algorithmic building blocks. Over the past 15 years or so, or more, 20 years, many algorithmic components have been created to achieve very good, very accurate privacy-preserving algorithms that satisfy this differential privacy definition. Now, this is all good, but one keyword, the one I emphasized before, is randomness. These algorithms, just inherently to satisfy this definition, need to be randomized. And that comes with great guarantees, the privacy guarantees, but at a cost. Essentially, we need randomness. And that might not sound like a big deal by itself, but randomness is not free. Randomness is not something we can or should take for granted. Typically, computers are bad at generating randomness, and randomness can be imperfect, hard to trust. It can be expensive, hard to generate. And that is often a bottleneck in terms of security or computational aspects. Generating enough randomness that you can trust can be a key issue. And generally speaking, I think seeing randomness as a resource is a very fruitful and important way to think. Now, this is not just a theoretical aspect, even though it leads to a lot of very interesting theoretical problems. This is a quote from Garfinkel and Leclerc from 2020, based on their experience of differential privacy being deployed in the US Census. And what they write is, we estimate that the 2020 census will require roughly 90 terabytes, this is the actual number, of random bytes to protect the person and household tables that the US Census is outputting. The need to generate a large number of high-quality random numbers is a largely unrecognized requirement of a production differential privacy system. So again, this is a pretty long quote, but what this is saying is we can't just ignore and sweep under the rug the fact that just to ensure things are differentially private, we need a lot of random bits, and we need to generate them fast, and we need to generate them in a way that we can trust. Which brings us to the key question that this paper and this work are about. Essentially, it can be framed that way. How much randomness is needed to ensure differential privacy? And not just that. It's not just like, is there a threshold? It's also, is there a trade-off? Is there a fundamental trade-off between what we want, algorithms to be accurate, what we need, algorithms to be private, and what we must get, the amount of randomness? And if you only get this out of this talk, the key takeaway is there is a trade-off, and it's very interesting, both theoretically and to play with. There's a deep connection to geometry and to some recent works of Van der Voorde, Dixon, Pavan, Radcliffe, and Vinochandran from the past couple of years on what they call deterministic rounding schemes and secluded partitions. So if you want to explore that in more detail, this is both very interesting mathematically, philosophically, and also leads to a lot of interesting ideas to be played with. Now, as I said, this work introduces the study of differential privacy from the point of view of how much randomness is needed. We start with a very basic fundamental task, data summation. What does that mean? So we have n users. Each of them has a lot of binary attributes. So D is a dimension. Each user, each of them, has D binary attributes. See that as a vector. What we want to do is to privately estimate the sum of those n vectors, which is a d-dimensional vector by itself. And what we want is estimate each resulting coordinate to small infinity error. So we want for each coordinate of the sum to have an accurate estimate. Now, the good news is we know how to do this. This is not a new problem. This is, as I said, a fundamental problem. One of the most basic techniques in differential privacy add some Laplace noise, independent noise to each coordinate of that sum. So first compute the sum, then add some noise. Carefully calibrate it, so with some mean and variance, like mean zero and variance that depends on the privacy parameter epsilon. That suffices to ensure differential privacy. And actually that is enough to ensure the optimal accuracy for a given privacy level. So that's all and good. Laplace noise is continuous. If you don't like this, you can also use geometric noise. You have similar guarantees with that. The only issue with this is you have D coordinates. You add some independent noise to each of these D coordinates. You will need at least omega of D random bits. This is just inherent to this approach. And again, if D is really large, that is a lot of randomness. So the question is, can we do better? Does it need to scale linearly with the dimension? Now, I kind of spoiled the surprise in this slide. We can do better. It is actually possible to do a lot better than a scaling that is linear in the dimension, which came as quite a surprise to us, or at least to me. Here's the theorem we prove. So we're going to take a little bit of time to parse this. But essentially, for every target parameter L you have, there is a differentially private mechanism M that takes in a database of N from N users, each of them having a vector of D binary attributes. And this mechanism has expected randomness complexity that is upper bounded by this beautiful quantity. So D over L times log L plus some constant overhead, and achieves accuracy. Again, forget about the big O tilde, which hides a logarithmic factor, but D times L over epsilon. And again, remember that essentially D over epsilon is the best you can do. So maybe to set things up a little bit, if you take L to be D, this is what you get. Log D, randomness complexity, expected randomness complexity, and accuracy D square over epsilon, which is not optimal, but is independent of N. So does not depend on the number of users, which might already be kind of surprising. You do not have to pay a linear number of bits in the dimension. Logarithmically in that is enough. and you still achieve error that is polynomial in the dimension and has no dependence on the number of users. Now, due to time constraints and the format of this talk, I am not going to talk about the rest of the results we have. I'm going to focus on this one that I just briefly flashed to you in this slightly informal way. But we also have an upper bound for approximate DP. So if you already forgot what that is, don't worry. But this is when I have two parameters, epsilon and the delta also is into play. And also we have a lower bound. So we have a lower bound that shows that this upper bound we just gave actually is not far from what you can, the best you can achieve. If you're curious, I encourage you to check the paper. I'm going to have the link at the end. But one interesting aspect of that is the lower bound and the upper bounds both use the same connection to geometry that I'm going to briefly talk about. Now, this key ingredient is, as I mentioned before, what's called a deterministic rounding scheme, or equivalently another notion that was introduced in these two papers, PDPRE, secluded partitions. This is the definition of a deterministic rounding scheme. It has two parameters, k and tau, and rho as well. So what this is saying is for every input z, I apply my deterministic rounding scheme f to z, and I get a point that is not too far. It stays within the rho of the original point. That's the first condition. The second condition is actually also maybe a bit hard to pass, but what this is saying is, well, I don't have too many possible rounding representatives. So if I look at any ball, any L infinity ball around a point z, and an infinity ball of radius that depends on those two parameters, tau and rho, then the points in that ball will not be mapped to too many possible rounding representatives by my rounding scheme. So again, each of those deterministic rounding schemes will round inputs to points that are not too far. So they are rounding to things that are close, but also things that are close can only be rounded to a small number of potential candidates. That's the parameter k. Maybe more pictorially, and by the way, I need to emphasize that these beautiful figures, I don't have that kind of skills. So this is Francis who's doing, and check the paper for more of those amazing figures. So this is what this means. Here we have k is equal to 3. So you can see that I've got that tiling of the plane, tiling with those blue cyan squares. And inside each square, I have one possible representative, that purple point. And now if you look at any L infinity ball, that would be the slightly smaller purple square. Any point in there, no matter where I put this purple square, all the points in there can only map to at most 3 possible representatives. So then I achieve k is equal to 3 with this illustration. So maybe it's not clear a priori why this particular notion is very useful. We're going to go through how to prove the upper bound, the algorithm based on that. But think of it maybe this way. If I can round things in kind of a deterministic fashion, but so that I don't have too many possible outputs, then, well, that bounds the entropy of my algorithm. No matter what I do, if I have few possible options that I can output, then I don't have much more than log, or I actually have at most log of that number of things in terms of entropy for my mechanism. So that's the key insight there. So here is the full algorithm behind the theorem. So first we set some parameters. So we have to set those parameters tau, k, and like some radius r. So we set them according to, you know, that L that is an input parameter, D that's the dimension, and epsilon that is our target privacy parameter. Don't worry too much about why we set them that way. Hopefully that's going to be clear from the next few slides. But we set those parameters. And then what we do is, well, we have that parameter k, we have that parameter tau. Let's just find a good rounding scheme. So, you know, based on previous work and like some things we also do in our paper, they exist. So I can get a deterministic rounding scheme F, which has those two parameters to parameterize it. Now, okay, so what I do now, well, I'm going to compute that sum of x, which is the thing I want to estimate. So I compute it, and I just add some noise to it. I literally apply that Laplace noise I said was the basic idea, like the fundamental idea that you would use just left to yourself. So let's just do that. I compute sum of x. I add carefully calibrated Laplace noise just to ensure privacy. Then what do I do after this? Well, I'm not done. I'm just going to round that to the nearest multiple of r, that radius parameter r, times tau. So instead of having something continuous, that allows me to like bound the entropy a little bit better. I'm just gonna run that on the grid. So I get at this point a point y, which is the sum I want to compute plus some noise, all that rounded on a carefully suitably fine grid. At this point, I remember that I have my rounding scheme f, so I'm just gonna use that f on y. So I compute f of y, and that's all. I output f of y. This is the whole algorithm, and we have a few things to prove. First thing we need to prove is it's actually private. The second thing we need to prove is, well, it's accurate enough. You know, f of y is not too far from sum of x, the thing I want to compute. And finally, it would be nice if it used not too much randomness, because that's the whole motivation for what we're doing. So then we're going to bound the randomness there. And you're going to see there's a little bit of a catch. But again, more pictorially, this is what the algorithm is doing. So I start with the thing I want to compute, that red annulus in the middle, and I add some noise. So I add some random noise around it. So that's like point cloud around it, the red point cloud. And the idea is like, well, unless I'm very unlucky, I'm adding some noise, but it's not going to go too far around there. So it should still be relatively close. So I get to that triangle, red triangle there. Well, after that, I round. So I get to that square, the red square on the grid. And finally, at this point, I remember I have my deterministic rounding scheme. So I just use it to get to that purple point there. And I output the purple point. So this is the algorithm. This is the whole algorithm. From the red annulus, add some noise, get to the red triangle. From the red triangle, round it to the red square, and then apply the deterministic rounding scheme to get to the purple circle. First, I claim this is indeed private. Why is that? Well, we started by computing the sum, and then we add some noise, carefully calibrated so that using the Laplace noise, this is private. So sum of x plus eta, that noise, that whole quantity satisfies differential privacy. This is just using, again, those building blocks we know exist. Nothing particularly new there. Of course, this thing is private, but this is not exactly what we are outputting. But after that, all we are doing is looking at that quantity and post-processing it. And there's that amazing property of differential privacy, which is if something is private, you compute something privately on your data. Whatever you do after that, as long as you don't look at the original data anymore, you can post-process it any way you want. This is still equally private. The privacy does not disappear. So by post-processing properties of differential privacy, the whole thing, whatever I do to sum of x plus eta after that, so in particular, what I'm doing here, is still epsilon private. So this is good. That establishes 1/3 of what we want to establish. Then we want to establish that this is accurate enough. So I'm ignoring a log here. It's going to come back next slide, but think of that as like dl over epsilon, just for intuition. My estimate f of y with I probability as L infinity error dl over epsilon. And why is that? Well, again, what did I do? I started with the thing I wanted to compute, and then I added some noise to it. But that noise, well, it's Laplace noise, so think of it as noise that's like well concentrated. So with high probability, I don't get too far from it. And what does that mean too far? Well, that means dl over epsilon times log d. So just adding that noise does not get me too far with high probability from the estimate I want. And what do I do after that? Well, after that, well, I round it to a nearest point on the grid. And based on the parameters I chose, that's not going to lead me too far astray. So I'm still close enough. And what do I do after this? I apply this deterministic rounding scheme. But the first item of a deterministic rounding scheme is, well, it's rounding to a point that is not too far. So I started with something, I had some noise, I don't get too far. I round it, I'm still not too far. And then I apply the deterministic rounding scheme. That doesn't send me too far either. Overall, I'm still close enough. And by close enough, I mean the error I claim here. Which brings us to the third point, which is really the key. This on input X, any database X of n users' data, each of them being the binary attribute, the outcome of this algorithm has support with high probability at most k, for that k that is defined in the algorithm. So for each input X, the output with the high probability output of this algorithm has small support. Now again, why is it the case? It's gonna sound very similar to what I said before. We start by saying I added noise. Okay, so I added noise to sum of X. I don't get too far. So at this point, I am within a small ball, small-ish ball of some radius. What is that radius? Roughly dl over epsilon times log d around sum of X. This is just because the noise doesn't lead me too far. Again, I round. I'm still roughly in that ball around it. And then I apply the deterministic rounding scheme, and now I'm using the second item of a deterministic rounding scheme, which says, well, if I look at any small enough ball around any point, f of that, the image of this ball by my deterministic rounding scheme, has small cardinality at most k. This is exactly what I want here. So just by definition of the deterministic rounding scheme, I get claim number 3. Just to be completely accurate, here's the extra log d that I was hiding for intrusion. Anyways, at this point, we're almost done. We have proven that what we have is epsilon dp, that it has good accuracy, and that it has small support. Now, with high probability. If something has small support with high probability, then its entropy and its expected randomness are also roughly log of this. So at this point, it seems like we're good, except that claim 3 is actually lying quite a bit. What I just said is actually wrong. If you look at our algorithm, it actually uses a lot of randomness. I mean, it literally samples from that Laplace noise and add that noise to it. So this is exactly the algorithm the naive algorithm that uses a lot of randomness, except that like we post-process it afterwards. So why are we doing all this? Well, here we can use this known fact, which is just, what we did is to bound the entropy of the whole algorithm. So if I look at my algorithm as a full black box, what claim 3 is saying is this has small support. It's still using a lot of random bits inside, but as a whole, it has small support. Now, there's a classic result in information theory that is based on like Huffman coding that says that you can take this algorithm and convert it to something that is basically equivalent, but only uses a number of bits on expectation that is related to its entropy. That is its entropy. So you can compress our algorithm that is simple but uses a lot of randomness into an equivalent algorithm that uses much less randomness. We just don't know exactly what it looks like, but it is possible to do it. It's an existential result. And so at this point, we're done. This final algorithm that exists is exactly the one that satisfies claim 1, claim 2, and has small expected randomness complexity. And this is the one that establishes the theorem. So this is all I wanted to say here. Again, check the paper for more results, upper bounds and lower bounds. I also wanted to mention summary and future work. This is meant as initiating the study of the randomness complexity of differential privacy. There is a lot more. We barely opened the door to this study. If you're interested in high-dimensional geometry, by all means, this is a very interesting connection, two ways, both for upper and lower bounds. It would be great to explore it further. Now, in terms of future directions, closing the gap between the upper and lower bound, there's still a polynomial factor. We don't know if it's necessary or not, would be very interesting. Taking a step back, having a more general systematic treatment of this study of randomness for DP would be also, I think, very interesting to have. So here we focused on the task of summation, but either you could generalize that to more tasks or have just a systematic treatment of the whole algorithmic aspects. Efficient algorithms, it's just, that last step from the previous slide where we take the algorithm I just gave and convert it into an equivalent algorithm. This is not an efficient transformation. It'd be nice to actually have an actual efficient algorithm that achieves the same things. And finally, and thanks to Mark Ben for pointing out to us this connection, there are some connections to another recent area, replicability for learning and algorithms. And there seem to be some interesting connections there. Exploring them further would also, I think, be very fruitful and very interesting to do. And this is all. Thank you for listening. If you're interested in the paper, there is a QR code, but also just a URL if you don't like QR codes. Thank you.